Alright, hello ladies and gentlemen. Today we're going to be working on some exponential and log equations and applications. So, before I get into the applications, we have to be able to solve equations like what we have here. Alright, e to the 3x minus 2 is equal to 24. Now this is not going to be something nice. E turning into 24 isn't simple, but we can solve this using logs, using a calculator, and so on. So, when you get an equation where it's e to the something, here it's e to the 3x minus 2 equals to 24 on the other side, what we can do is use to get rid of this e to the power, right, to undo that exponential and to bring down this exponent up there, we can use the inverse operation. So if e to the x, its inverse is natural log, we can natural log both sides of this equation. And of course, the natural log and the e cancel each other out, bringing down that exponent to get 3x minus 2 is equal to natural log of 24. Now, natural log of 24 is just like a simple decimal. You can plug it into a calculator, or we can solve it the way it is. We can add 2 to both sides, get 3x equals natural log of 24 plus 2, divide by 3, x equals natural log of 24 plus 2, all over 3. And using a calculator to figure out the value, if this was, an online homework assignment, you could honestly just type it in like that, or you can use your own calculator to see that this value is approximately 1.726. It's actually a decimal that keeps going on and on and on and on and on. All right, so that is an exponent that when you plug it into that original expression should work. All right, for a similar example but having to deal with logs, take a look at this equation. So before we had an exponential in the equation and we used logs to undo it, now we have a log in this equation, this log of 3 of x minus 4, and we're going to try and undo that. But to get there, you first have to get rid of the addition and subtraction and the multiplication outside. So we're going to start this by subtracting 1 from both sides of that equation. 2 log 3 x minus 4 is equal to 30. Then we're going to divide both sides of this equation by 2. Log base 3 of x minus 4 is equal to 15. Now, how do we undo this log base 3? Well, it's with an exponent of base 3, so we're going to exponentiate both sides of the equation with a base of 3, same as the base of our log. Of course, on the left-hand side, the 3 and the log base 3 are going to cancel out. We just need to make sure that when we get our solution, we're not allowed to have a negative in there, right? Because we can't do log base 3 of a negative number. So 3 raised to the log, 3 raised to the log base 3 cancels out. We get x minus 4 is equal to 3 to the 15th. Add 4 to both sides. We get x equals 3 to the 15th power plus 4. Now that's a very, very large number. And I get something like 1,434,8,911. So that's 14,348,911. All right, and so that's how we can use logs and this property of inverses in order to solve log equations and exponential equations, right? If you are solving an exponential like we did up here, when you get the exponential by itself, we can log both sides, make sure we use the same base as the exponential to cancel out. And down here, get the log by itself, then we exponentiate both sides to cancel out the log, okay? Very easy for solving. Now we're going to be doing that by applying that idea to growth and decay formulas. So, to review, There's a couple different formulas we should know. The first formula I have here comes from basically simple interest. It's about percent increases and percent decreases. So A of t, the amount after a time t, is equal to p sub 0. P sub 0 is always our starting amount in all of these problems. T still represents time. And R is going to be our growth percent. Sometimes they call it a growth rate. That's, of course, if it's the positive version. We're adding on 1 plus R would be growth. And, of course, a decay where you're decreasing some percent would be if that value there is negative, where you do 1 minus the percent, and so on. We just have to make sure that this rate, whatever time period the rate is, if it's per annual year, it's per year, then time has to be in years. If it's per 10 months, then your time is going to have to be adjusted for 10-month periods, and so on, okay? A second type formula is doubling or halving time formulas. And we saw this before, right? A doubling time, you take p sub 0, your starting value, and you multiply it by 2. And then for the exponent is t over h, where h, in the first case, is your doubling time. Keep in mind, though, if your doubling time is, say, 3 months, then t that you want to plug in has to be in months as well. You got to keep those time periods the same, okay? And you'll see that in the example problem I do. In the second formula here, h is the halving time. Okay? As we solve these, sometimes we're going to be solving for the exponents, and when you solve for an exponent, you're going to have to log both sides of the equation, okay? Alright, now, the more common growth and decay formulas, things that you're going to be seeing in like science classes and AP biology and so on, is they don't like to use 2 as a base for doubling or 1/2 as a base. They prefer to use a base of e. Now, when we get to calculus and we study exponential functions, their derivatives, their differential equations involving exponentials, it might become more clear why we like to use e for you, but right now we really just like to use e as our base, and you're going to see that in a couple of the problems. Here we have the formula for growth. A of t, the amount at time t, is equal to p sub 0, our starting amount, e to the kt. This here is growth because your k is positive, right? K is greater than 0. This is called our growth constant. In the second formula, you can see the negative up there with the exponent e to the negative kt. This k here, you know, our k value is still positive because you have the negative in front, but we would call k here the decay constant. Okay, so now growth rate is your percentage, and that's part of the simple interest formula that we have up here in Formula 1, and decay and growth constant is part of that exponent, e to the kt. And you can actually solve and go back and forth between doubling time and this exponential model, this with e as your base, okay? So look, I'm going to do an example here for you. About bacteria, this is a growth model. It's modeled by this formula, A of t equals 1500 e to the kt. Please note that if you plug in 0 for t, you get e to the 0 power, which is 1. You get 1500. Notice that's our starting. That's what we always put as our p sub 0 when we fill out these formulas. So now, it says it doubles every half hour. It's modeled by this formula. And it says find the number of bacteria after 110 minutes. Now the first task that we have to do here is we have to find K. we have to find the growth constant. And we're going to use that. I want to make this minutes. So half hour, we're going to make our time in 30 minutes. All right. So T is going to be in minutes from here on out. Okay. So we're going to use that after 30 minutes, the population has doubled to 3,000. So I'm using this kind of initial condition, this point for our T and our A of T, and I'm going to use that to solve for K. So 3,000, the population is doubled from the original 1,500, e to the K times 30, okay? And now we want to solve and find that growth constant. So first thing I'm going to do is divide the 1,500 over. Got to get that exponential by itself first. And that means 2 equals e to the K times 30. Now that we have that by itself, we are going to log both sides, right? We want to cancel out that e to the power. We want to get rid of that. So we natural log both sides of that equation. The natural log and the e cancel. We get natural log of 2 is equal to K times 30. We can divide that 30 over. And of course, our growth constant is going to be natural log of 2 divided by 30, which is 0.02310. Okay, so I'm going to use that now as part of our formula. A of T equals 1,500 e to the 0.0231 times t, right? And we want to know what is the population after 110 minutes. So the second task here is to find A of 110, 1,500 e to the 0.0231 times 110. Just simply plugging in for that exponent, that time, and in WebWork you could just go ahead and plug this in. Otherwise, you can plug it into your calculator, and you'll get about 19,038 bacteria. Okay, so that's how we use exponents to solve some of these equations. Please try the WebWork assignment on exponential and log equations and applications. And when you're finished with that, I'll be online on Tuesday to try and help you out with any questions. But when you're done, you can move on to the trig and see if you can remember some of that right triangle trig from geometry. Thank you for listening. Have a good week.